let's now look at the thermodynamics of these nuclear processes, decay processes. Thermodynamics, remember, what we do is we study the different transformation of energy in chemical systems. How energy is given off, how energy is being absorbed in chemical processes. And this is particularly important in this case because one of the things, if you watch the video presented by the Energy Secretary Jennifer Granholm, one of the big things about these recent discoveries is that they may open the door to solve the energy crisis or problems that we have. But the big question is, at least I think for the public, would be, where does all this energy come from? To answer that question, we're going to look at an example of what happens when we combine two protons and two neutrons to form a helium nucleus. Remember that nucleus, helium nucleus, has two protons and two neutrons, and that's why the atomic number is 2 and the atomic mass would be 2 plus 2, 4. If we look separately at these protons and neutrons and we look at them together in the helium nucleus, we come across something that it's quite interesting and gets our attention, and that is that the mass is not the same. The mass of the quote-unquote reactants is not the same as the mass of the product. If we multiply the mass of a proton times 2 and add that to 2 times the mass of a neutron, the mass of a proton and neutron are very similar. If we add them together, we get this value down here. But when we look at the helium atom or nucleus, its actual mass is this value that we have here. All of these values are extremely, extremely, extremely small, evidently. We get that there is a loss of mass. Those masses are not the same. That difference, we call it the mass defect, the loss of mass. So there's a change in the mass, which is something that intuitively we would not have expected. So what happens here is that some of that mass of the separate nucleons becomes energy, is given off as energy when they come together and form a more stable species, which is the helium nucleus. How much more stable is that helium nucleus? That is how much energy is given off. Oh, before we move on, just as an exercise, it may be that you want to find the mass change or mass defect for a mole of helium. Because here what we have is just 2 protons and 2 neutrons to form 1 nuclide of helium. But what would be that value if instead of just 1 isotope, 1 particle, we had 1 mole of particles? Okay, just a conversion exercise. So how much more stable would that be? Thank you, Einstein. We will talk more about this equation when we cover chapter 12. But as of for now, what it tells us is that there's an energy change associated with a change in mass. That would be the same as saying that, or it would take us to say that that energy is a manifestation of mass, or vice versa. Mass is a manifestation of energy. So they're interconvertible. And they're related by the square of the speed of light. So let's take this example one step further and try to find that amount of energy that's released. We're going to take this mass defect for one nucleon, for one nuclide, I'm sorry, we're going to take this mass defect. It is expressed in grams here, and here I have the same value but expressed in kilograms, so that's why the exponent changed. And the negative sign is just to remind us that this is a change in mass. It is decreasing. The mass itself cannot be negative. Evidently, mass cannot be negative for our calculations and purposes, but the change in mass can be negative. So we take that mass and we multiply that mass change times c squared. We get this value. The units of the product will be kilograms times square meter over square second. It is very important to keep track of your units, because if you don't, you're going to mess up. So another expression for this group of units is joules. They're equivalent. So this would be the change in energy for one nuclide. Forming just one nuclide of helium-4 would release this amount of energy, and the negative sign reminds you that this process is exothermic, energy is given off. Now another question we can ask is, how much energy would be released if instead of looking at one nuclide, we look at each nucleon within that nuclide? And that's why it's important to understand, recall, remember the different terminology. Nuclide would be the entire helium-4 nucleon. Each proton, each neutron would be one nucleon. So helium has 4 nucleons. We take the amount that is released for the entire helium nucleus and divide it by 4 because it has 4 nucleons, and we get a measure of how much energy is released per nucleon. Since that energy is being released, that means that the system will be, the product will be more stable. So it is stabilized by this factor per nucleon. We prefer to use mega electron volts as the units. So we have a conversion factor here. We apply the conversion factor and we get the same quantity expressed in mega electron volts per nucleon. This is the stability gained per nucleon in the case of helium-4. And we call this the binding energy. And it is expressed per nucleon. The value up here would be the binding energy of helium-4, and divided by 4 gives us the binding energy per nucleon for helium-4. We divided by nucleon as a way to standardize, normalize the values so that we can compare values for different nuclides. And that is exactly what we do here. Notice that this value here is negative because the system is being stabilized, but what we call the binding energy is actually the positive value of this that we get. So that we understand this plot. In this plot we have the binding energy per nucleon and the mass number. So we have different isotopes or different nuclides here, and we have the corresponding binding energy per nucleon for each one of them. And that's again why we normalize it. We do it per nucleon so we can plot all of them together and we can compare them reasonably. So we have hydrogen-2 here, deuterium, and uranium-238 up here, for example. We see that the binding energy increases in this direction, reaches a maximum, and then goes back down. The higher the binding energy, the more stable the nuclide, okay? Because the particles are going to be held together more strongly. So that means that Fe56 is at the top of stability in terms of nuclides. Here we have helium-4, and the reason why I have it pointed here is because you see it's above 7, the value for the binding energy per nucleon, which means somewhere I made a mistake because I got here 6.8. So you may want to revise these calculations and see if it was that I used an incorrect conversion factor, or that I did not round off properly, or my significant figures. Just check those calculations, because we see that value should be a little bit higher. Okay, and one thing that this plot tells us, we always interrogate our graphs, is that lighter nuclides, they may tend to become more stable by combining more than one nuclide. That is, through fusion, combining, merging nuclides to get a heavier nuclide. Whereas the heavier nuclides themselves, they will become more stable if they split into more than one nuclide. And that's the process that we call fission. So we have fusion, lighter nuclide combining to form heavier, more stable nuclides. And we have fission, heavier nuclides splitting into more than one stable or more stable nuclide that will be necessarily lighter. Those are the two processes. And now we're going to stop and practice. Here we're going to use this plot to answer a few questions. We're going to explain fission and fusion, why both of them are exothermic. So do not just memorize things, but try to explain why would those processes be exothermic, which explains our interest in fusion currently to solve the energy problems of the planet. What is the approximate binding energy per nucleon of carbon-12? We do the same, but this time for one nuclide of carbon-12, and then for 1 mole of carbon-12. And then we're going to predict what happens with tin-119. Would it undergo fission or fusion? And just, more than just saying which one, explain what leads you to that conclusion. We've got a calculation here, and for this calculation of binding energy, I'm using atomic mass units here. You can use other units if you want. This is to practice also conversions, but the result will be the same regardless of the units that you use. Is this reaction fission or fusion? And number 7, do you see is there anything particularly interesting about the products in this reaction? When you look at the products in this reaction, you look at the full reaction, and then you look at the products and see if there's anything that gets your attention, and that's going to help you with the next